Hi all, thank you for tuning into my channel. This is section 6 of the course. I realized that the whole of section 6 put into one video makes it very long and high storage value, and it was difficult for me to upload. So what I have done is separated 6 into two sessions, 6A and 6B. In 6A, we'll be dealing with fundamental chemistry on carbohydrates, fats, and proteins, a nucleoprotein, and some parameters. Please note these are just simple information, and if you do need to know more about it, you will have to look into the internet. You will get more than sufficient information. It is necessary for you to know a little bit on the chemistry and the structure of a molecule or atom, so that you'll be able to understand as I go through the course as to how each element or each chemical reacts with the other. The first thing is we have to learn that an atom of an element consists of a neutron, which is a heavy particle, proton, which is positively heavy particle, that is positive. The nucleus contains of these two, and around the nucleus will be circulating groups of electrons. The electrons will start initially 1 to 8. That's the maximum in that orbit. And then it goes to a bigger orbit from 9 to 16, and still bigger orbit 17 to 32. This way, the number of electrons can increase in an atom because the weight of the atom depends on both the neutrons and the protons. As the neutron and protons increase, the weight also increases. The proton carries the positive charge. So if there is a higher number of positive charges, then you have a higher number of protons. Now, there is also information that the nucleus will tend to be in pairs as much as possible, because that gives them some stability. But if they are single, then they will try to react with another atom or electron of another atom, join them up, and becomes a double pair. This is how many of the reactions take place in between two atoms or two molecules. As I did mention to you that the atomic weight of any element depends on how much of neutrons plus protons in the nucleus. Because the weight of the electron is so minute, it hardly has any effect on the atomic weight. Now, all the elements known to humans have been classified according to their number of electrons or protons in each of the atoms. The hydrogen atom has got one proton and one electron. Helium has got neither protons nor electrons. Because of that, helium is a very, very stable gas. It doesn't react with anything. Now you go back to number 10 on the table, you will find that neon also has got 0 zero electrons and zero, or neutralized zero protons, which means it's also neutral and is also that is not very reactive. They are all grouped together, which is called a group of non-reactive gases or rare gases. You notice that lithium has got one proton, beryllium has got two protons, boron has got three electrons swirling and three protons. Lithium has got one electron, which is available there. Beryllium has got two electrons, and carbon has got two protons and four electrons. And nitrogen has got the multiple numbers depending on how it is present in the system. Oxygen has got two electrons. Fluorine has got one electron and one proton. Neon has got zero, as I said before. And then sodium goes back with one proton. You will notice that lithium and sodium are very similar. So they come under the same group of chemicals. Likewise, chlorine and fluorine also come from under the same grouping. And they are called the halogen groups. The table proceeds further from silicon, phosphorus, sulfur, etc. They all increase in atomic weight. As you go further down the table, you find the atomic weights increase. Obviously, the number of protons which determine the positivity and the number of electrons that determines the negativity of the atom. Most of the atoms chlorine to chlorine are negative, and most of the atoms closer to potassium, lithium, etc. are more positive. I just gave you some information on the periodic table and how the atoms are structured. If you would like to know more about it, I would guide you to go into the internet, and I'm sure you'll be able to find more details on how these atoms function or how the protons are situated and how the electrons are also spinning around each of those atoms. Now, we have two types of chemistry. One is inorganic chemistry, and the other one is organic chemistry. In the case of the inorganic chemistry, we will be looking into reactions between atoms other than carbon or molecules other than carbon with the rest of the other elements. In the case of organic chemistry, because, excuse me, organic chemistry is typically a chemistry totally consists of carbon compounds. It's so huge. So it is considered on a different setup called organic chemistry. Now, in the inorganic chemistry, what we will be dealing mostly will be the ferrous or ferric, sulfides, halides, in fluorine, chlorine, nitrous, sulfur, phosphorus, chemicals, etc. We will be also dealing a little bit on heavy metals because some of those heavy metals present in our waters are very hard to remove, and we have ozone to assist in removing them without much help or difficulty. In carbon chemistry, you've got carbon has got a four bonds, four, as you know, that four electrons. Each electron can link with another electron to form a stable combination. Likewise, the four single electrons can combine with four single electrons of another compound or element to form a compound. Sometimes carbon itself links with another carbon with two bonds, which means there will be only two more electrons left to form two combinations with this bonding. Likewise, carbon can have a triple bond. In other words, three of its electrons can be linked together to form stable compound. So there are only one for each of their carbon, which uses to react. In the case of nitrogen, you have a carbon-nitrogen link, you have a carbon-sulfur link, and the long chain compounds that have these bonds are very important in ozone chemistry. Ozone cleaves carbon sulfide, carbon nitrogen, etc. bonds. The aromatic bonds are actually cyclic compounds of carbon. In other words, for example, in benzene, you've got 5 carbons linked to each other together in a circle. And then the other 2 links available of the carbon will react with other elements or atoms. This slide has got 2 sets of chemicals. One is carbohydrates and the other a polypeptide chain. Carbohydrates means actually is carbon, hydrogen, and oxygen. In other words, the carbon is linked up with hydrogen, oxygen in different forms to form carbohydrates. If you look further, I have given a simple structure of a monosaccharide or glucose. If you notice that this is a long chain structure which has got 6 carbons with each carbon linking with a hydrogen or hydroxyl grouping. The 6th carbon will have a oxygen and hydrogen grouping. That gives you a ketone grouping, you call it. The glucose molecule can also link in a chain form or in a ring structure linked by the oxygen. If you notice that you've got your 6 carbons are joined together by one oxygen. This is not an aromatic compound because in aromatic compounds you have all the 6 will be linked together by carbon and not oxygen. Sugar, or in this case glucose, can form other type of structures, or they have got both structures, which we are not intending to go further. Now, with respect to the proteins contains a series of polypeptides, which itself is a chain containing amino acids. The amino acids are actually small little compounds containing carbon, hydrogen, and nitrogen in the form of NH2 or amine. Now, each of the colored balls are different types of amino acids. They are linked together to form your polypeptide chain, and the polypeptide chain can link together further to form a protein molecule, which can be thousands of chains of polypeptides. This figure shows the structure of fats. You notice these fats or fatty acids, I would say, are long straight chain compounds or aliphatic compounds. They are just linked to each other by the carbon group. If you also notice, there are two yellow markings in linoleic acid, one in oleic acid, no yellow markings in palmitic acid, no yellow markings in stearic acid, and no yellow marking in linoleic acid. Where you see the yellow markings, if we look a bit closely, you find the carbon links are double bonds. So if you say find that linoleic acid two sets of double bonds, oleic acid has got one set of double bonds, and linoleic acid has got also three sets of double bonds. So you will find that linoleic acid that is linoleic acid, is the most unsaturated between the three of them. Now, palmitic acid and stearic acid you will find doesn't have any double bonds. This means they are called saturated acids. Now, all acids in our fatty acids will have a link. If you notice on green, COOH link. This COOH link means it's an acid. This slide gives a picture or a diagram of what a fat is. The fat is alternatively known as triglyceride. If you notice that triglyceride means glycerol has got three hydroxyl groupings, and it combines, each of the hydroxyl grouping combines with a fatty acid. Now, this triglyceride, which is called an oil, can be hydrolyzed generally with sodium hydroxide, which automatically releases the glycerol, which is a OH grouping, and fatty acids are released. And fatty acids are generally insoluble and they can precipitate out. But the sodium hydroxide can further react with your fatty acid, COOH group, to form COONA, that is a salt of a fatty acid, and the salt of the fatty acid is what you call soap. This diagram is an important diagram. I am giving you fundamental oxidation reaction of organics, and any oxidation takes place, if at all, by the breakup of the bonds. There are three types of bonds in between carbon. One is a carbon-carbon single bond. The first one is carbon-carbon triple bond. That means 3 links, as I did mention earlier. The second one is carbon double bond. For example, when ozone reacts with a carbon triple bond, it breaks up one of the links and eventually forms a OH. There are 2 OHs for each of the carbon, one for each of the carbon. The double bond can further break up or broken up by oxygen, oxidized by oxygen you will call it, so that it will be a single bond and you will have another set of hydroxyl OH bonds formed. So altogether you can have 4 OHs. When ozone reacts with any of these combinations, all it does is releases the atom and it reverts to oxygen. Now, there are some interesting bonds, which you call them conjugated. It means you find the carbons are linked with one single bond, the next one double bond, the next one single bond, and the third one is double bond and single bond, etc., etc. So because they are single double, etc., they call it conjugated bonds. These conjugated bonds are found in smells, is found in colors. So each color or each smell has got a specific set of single or double bonds in a conjugated form, and each structure has a different smell. The diagrams on this side gives 2 pictures, one of a monosaccharide, which is a carbohydrate, and the other one is a amino acid chain, which is a polypeptide chain. Now, in the case of carbohydrates, it's defined as it has got a carbon, hydrogen, and oxygen. So it's got you'll notice that in the long chain structure on the left picture is that of a monosaccharide structure, which is a sugar or glucose, and it has got the hydroxyl grouping and hydrogen grouping together with a COH grouping. And the last carbon has got a CH2OH, which is actually CHOH. Now, on the right side of this figure, you have a cyclic structure of a sugar, which is, you find that it is joined together by O. In other words, a double bond O in the left will just link up with the CH2OH on the end to produce a ring structure. This is not an aromatic structure of aromatic compounds which have all the 5 carbons linked together, not linked by 4 carbons linked with, I would say, all 6 carbons linked together, not as it shows in the ring structure where there is 5 of the carbons are linked together by a oxygen group. Now in the second picture where the amino acids, we find that there are 4 different colors. That means there are 4 different types of amino acids. Each of them are simple 4 carbon chains which contain a amino grouping, which is an NH2 grouping. As that you call them amino acids, and these amino acids can be linked together by their carbon chains to form a polypeptide chain, and polypeptides can link further to form protein chain. So they can form a very, very long, complex chain with each other, forming proteins. This slide composes some of the smells. Besides the smells of organic compounds, which also have got double bonds, the one I explained to you were the long chain bonds, and double bonds also can give smells and odors like the long chain bonds. In halitosis, you find it is a sulfur compound with oxygen, with carbon, and you have the aromatic substances. The way you call that aromatic is because you get some smell on it, and they are like benzaldehydes, vanillin, ethyl benzene toluene, ethyl hexanol, etc. Benzaldehyde, vanillin gives you some pleasant smell. Ethyl benzene toluene also does give a good smell, and ethyl hexanol is a floral smell. You notice that nicotine also has got carbon-nitrogen bonds, and it may not give smell, but it has got a effect on our nervous system. Now, one of the important things is ozone can break up nicotine smells, and therefore remove them. Viewers, thank you very much for having the patience to listen to me. I have come to the end of this session 6A, which are fundamentals in biochemistry. If this is for your first tuning in, please visit sessions 1 and 2, which gives the program details, and 3 to 5, that gives you history of ozone and fundamentals in chemistry, etc. I would appreciate if you please click the like icon, and preferably it's a subscribe icon, so that you will be notified of the next session as soon as it is uploaded. Thank you and have a good day.